We're talking about vectors, and this is a continuation of topic 1.4. So part 2 to that. And before we were learning about vectors and how a vector represents both magnitude and direction. So a number, the value, its units, and which way it's pointing. The length of the vector represents the magnitude, and the direction it's pointing, the direction. And we got used to some angle measurements, and we added vectors head to tail graphically. So sometimes the question, or many times, the question of components comes up. With vectors. And that's how much of a given vector is pointing in a certain direction. So you could take a vector, say like this, and it could have components in the x direction and in the y direction. Okay? This would be the x component, and this would be the y component, and this would be our vector. The components themselves are vectors as well. They have certain lengths to them. They point in certain directions. So, okay, let's make a little table. And for this table, we're going to have 3 rows, or 3 columns: direction, the x component, and the y component. Oops. Okay, and we're going to start with a vector. So we'll just take a vector like this. And let's think of our standard XY notation, okay? The XY, well, what's standard? And let's say that this vector that we have here is 1 unit long. How much of that is in the x direction? Right, 1 unit, sorry. The whole thing is 1 unit, and then 0 in the y. Let's take the same vector and turn it on end. Now, we have 0 in the x and 1 unit in the y. If we have the vector going this way, we'd say it's minus 1 unit in the x and 0 in the y. And then like this, I'm sure you can see is 0 in the x, minus 1 units in the y. Well, we don't need in the y part, it's already, whoops, minus 1 unit. Okay, so, but how about when it's in this direction, like that? Well, we could see we would have the partial one of x like that, and we would have the partial part of it in y, and both of them would be less than the 1, but we don't know how to get those yet. So let's learn. It has to do with ratios. So let's take this vector diagram and say we had a vector of 5 units. Well, no, let me put some, let's use meters because we'll get used to some different units. 5m for meters. And let's say it had a component in the x like that and a component in the y like that. I'm going to adjust, well, no, that's all right. It's not drawn to scale, so that's 3 meters and that's 4 meters, okay? And that's your standard 3, 4, 5 triangle, right? If you did Pythagorean theorem on it, 3 squared plus 4 squared equals 5 squared. So if we take that to our standard right triangle, actually, draw it a little more correctly. Our 3, 4, 5 triangle, like that, where that's right, that's our right angle. We can see that this side right here is 3/5 the value of the resultant, or the hypotenuse 5. And this one is 4/5 the value. It's ratios. Now it wouldn't matter how big the triangle is. We could take the triangle and there's a 3, 4, 5 again. Actually, there it is as 3, 4, 5, but we could double its size, right? Oh, come on. There we go. So we could take this and make it much bigger, so that now this would be 10, this would be 6, and this one would be 8, but it's still the ratio of 6/10 is still the same. 6/10 is the same as the 3/5, and 8/10 is the same as 4/5. So even though the sides of the triangle can change, the ratio of the sides for a certain triangle will stay the same no matter if you make it bigger or smaller. So as long as the angles in it stay the same, this angle and this angle are the same as this angle and this angle, and of course the 90 degrees one as well. If the angles stay the same, no matter what the size, little teeny or large, we still have the same ratios. Okay, so we call these ratios part of trigonometry. And we're going to learn a little trig in this class, but it's not anything to be too scared about. You'll learn it in math as well. And I'll show you the parts that you need to know. And we'll practice those as well. So let's take a standard right triangle. As long as it's got that right angle in it, we're good. Now let's look at this angle here. We'll call it theta. And we'll use that symbol theta. That's a common symbol. It's got a little squiggly line in it, like that. And this is called, it's the Greek symbol theta, and we use it for angles a lot. Okay. Now, in this right triangle, the side that's the longest across from the right angle is called the hypotenuse. The side that's right next to our theta, we call that the adjacent because it's adjacent to the angle. The one across from, it's adjacent to the angle and it's not the hypotenuse. The one that's across from theta, we call that the opposite because it's opposite side. Now, of course, if you take opposite over hypotenuse or adjacent over the hypotenuse or opposite over adjacent or any of those, you have ratios. And remember, for certain triangles with certain angles, there's certain ratios, and those ratios stay the same. So, if that's the case, let's take a look at what the value of these ratios are. So this brings us to the concept of trigonometry ratios. Well, and we're going to look at three common ones, okay? Now, the first one we're going to look at is the opposite side over the hypotenuse side, okay? What is the opposite over the hypotenuse? Okay, that's a ratio of values for this specific theta. And we call that a sine. We call that ratio sine. So sine for that angle theta equals the opposite side over the hypotenuse. And we shorten it by shorthand. We just say for sine, we drop the E, theta, O over H, opposite over hypotenuse, okay? And we call this SO. For sine, the sine of an angle theta is the ratio of the opposite to the hypotenuse side. Now, let's take another one. Let's take the adjacent. But in this time, we're going to put the adjacent side over the hypotenuse. And that is a different ratio, which is called the cosine. And the cosine of theta is just the ratio of the adjacent to the hypotenuse. And the side lengths might change, but the ratios for that specific angle in a right triangle will stay the same. And we shorten it cos theta, still cosine theta, pronounced that way, but when we write it, we shorten it, and it's A over H, ka, okay? And then the last one we're going to look at is when we take the opposite side and put that over the adjacent side. So opposite over adjacent. Now the opposite over the adjacent is something that's called tangent theta. Okay, so if you remember so, ka, toa, you can remember these three trigonometry ratios. And one way to remember that is, what do you do when your toe is sore? Soka, toa. Just remember, soka, toa, soka, toa. I remember my geometry teacher marching around and making us follow her around, chanting, soka, toa, soka, toa. Let's take a look at a new chart now, and this time with vectors again, and we're going to use these ratios. We have to use them in the calculator. Okay, we want to make sure we set our calculator to the degree mode for these as we do these. So we're going to make a new table where we have a direction of vector, we have the angle, we have the sine of angle, we'll just call the angle theta. So we have sine theta, cosine theta, tangent theta. So let's take one with an angle that looks like this, and it has an angle of 0 degrees. And if you plug into your calculator sine 0, you'll get out 0. And for cosine, you get 1. And for tangent, you get 0 as well. Okay? So if we look at this vector, the red vector here, we could see that the angle is 0, so there is no opposite side. So that would make sine 0. The cosine, the adjacent is the hypotenuse. So they're the same. So that gives you 1. So cosine is representing the x direction there. Let's take one all in the y direction. For that's at an angle of 90 degrees. Put that in there, you would get sine of is 1, cosine is 0, and tangent is not defined. And the reason that is because now our angle is 90 degrees, so now our opposite side is the hypotenuse. There's equal to the hypotenuse. So sine is 1 and cosine is 0. So, oops. How about this one? Well, that's at 180 degrees, and if you put that into your calculator, you'll get 0 minus 1 and 0, because it's all in the x direction at minus 1. And then if you put the 1 straight down, that's at 270 degrees, you'll get minus 1, 0, not defined again. So this allows us so we could see the other vector that maybe we were interested in. That looks like that. It has an x and y component. Well, let's say that angle was 40 degrees. Then the sine of 40 degrees gives us the component in the x direction of 0.64. The cosine of 40 degrees gives us 0.77. And the tangent is 0.84. So remember, this is a 1-unit vector. Okay, so now if we take our triangle again, where we had theta, the opposite, the adjacent, and the hypotenuse. We could and now we've written um, the trigonometry ratios, we could compare those to vectors, where we have a vector, a resultant vector. We have components of that resultant vector, Rx and Ry, and that's theta. Now, so looking at this, if we took this, the ratio of the sine of theta here, which is O over H, we could see the sine of theta equals the opposite, which is Ry, over the resultant, which we'll call R. So solving that gives you Ry equals R, but it's a vector, sine theta. And that is equal to, we want actually the magnitude only of that vector. So we put it in the bar, between the two bars. So here's a formula for the y component of a resultant vector. The x1 in the same method is now these with the bars and everything make it look confusing, but remember that this is the in the bars with the vector. So this part of the formula, this part right here, is just the magnitude of, or the value of your vector, your resultant vector. And to get the y component, you just take that resultant and you multiply it by the sine theta of the angle that it's there, okay? And for the x component, you multiply that magnitude by the cosine, okay? So it's really not too hard if you get over the fact that the formula looks so complicated. So let's take an example. So let's say, for example, you had a 40-meter vector at an angle of 30 degrees. And we ask, what are the x and y components of this vector? We could call this Rx and this Ry, okay? And Rx equals R cosine theta, and Ry equals R sine theta. And if we calculate that, it's just putting in 40 meters. That's the value, the magnitude of R, times cosine of 30 degrees. If we plug that into our calculator, making sure our calculator is in the degree mode, I'll enter 40 cosine parentheses, if they're not already there, 30. And that gives me 34.6 meters is the x component. And for the y component, it would be 40 meters sine of 30 degrees. Which would be equal to 20 meters. Okay? So of the 40-meter vector at 30 degrees, 34.6 meters in the x direction and the 20 meters in the y direction. Let's look at another example. So in this example, let's say we have a vector has a length of 220 degrees relative to the x-axis. Find the x and y components of this vector. Okay, so first let's draw it. Here's our x and our y. I mean our x and our y. And if we take a vector and draw it at approximately 220 degrees, it would be about there. That being theta equals 220 degrees. And I'm sorry, I left off a little piece. It was a length of 70 meters at 220 degrees relative to the x-axis. Sorry about that. Writing and not thinking. Okay, so to get the Rx of this, which would look like this would be the Rx component there, and Ry would look like that. Rx would be R times the cosine of theta, minus 53.6 meters, and Ry is R times the sine theta, minus 45 meters. Okay, there's your R, X, and Y components. How about adding vector components? For summing up or vector addition, we're going to make use of the Pythagorean theorem and components. So we did graphical. We'll call this algebraic vector addition. In the graphical representation, we needed a scale, we needed a key, and we need the vectors drawn in orientation, the angles with the correct lengths, and we placed each one that we were summing head to tail and then connected from the origin to the head of the last vector. Okay, so suppose we were pirates and we were told to follow a treasure map. Okay, and the treasure map said walk 20 meters east, or let's say paces, and then walk 40 paces north. Well, with north-east sort of system here, our path might look something like this. 20 paces east, and then 40 paces north. Okay? Our displacement vector is the one that starts at the origin here and goes to the head of the last vector. So this would be called our displacement vector. The distance we covered was 20 plus 40 paces, 60 paces, but the displacement is the value from the origin to where you ended up. Okay. So how can we solve for the magnitude and direction of this displacement? So how do we get the magnitude and direction of this? Well, we'll get the resultant, because that's what it is, isn't it? It's the resultant from the components. And if we look here, we know everybody's seen in math class, c squared equals a squared plus b squared, right? Pythag, the Pythagorean theorem. Now, for us, the magnitude of the blue resultant, call it R, the magnitude of that equals the amount in Rx, or the magnitude squared equals Rx squared plus Ry squared. Actually, let's make these ones red and green to correlate with our triangle that we formed up there, 20 and 40 there. So if I solve just for Rx, I'd have to take the square root of both sides. I mean, just for R, I'd have to take the square root of both sides. And I get R, the magnitude of R, equals, because the square root of the squared is just R, square root of Rx squared, plus Ry squared. Darn it. Sorry. And I have this formula here, which is important. That's just the Pythagorean theorem. And so for this case, it would just be, for our example, the magnitude of that displacement would be the square root of the 20 paces squared plus the 40 paces squared If I enter that into my calculator, I'm going to enter the square root sign, parentheses, 20 squared plus 40 squared, close parentheses, and I get 44.7 paces. That's just the magnitude of that resultant. The direction we haven't found yet, but remember those thetas. So we can get back to that, can't we? Looking at those thetas. The angle will give us the direction. Now, it can be noted that you could have a bunch of Rx's when you're summing these. And if that's the case, so if you have multiple Rx's, like this one, that one, even some others in the other direction, okay? And you have multiple RY's, like that, we can sum all of those together first. So to sum the Rx's, I should draw this a little better for the first drawing. That's what this means. It's a summation, meaning sum all Rx's. Over here, we're going to sum all our Y's. So, for example, if you had, what is the resultant you would first add up all your Rx's. So let's say that this was 3 meters, 1 meter, 2 meters, minus 1 meter, okay? And this was 1 meter, 2 meters, minus 1 meters. Then your summation of your Rx's would be minus 1 plus 2, minus 1, whoops, sorry, minus 1 plus 2 is 1 plus 1 is 2 plus 3, it's 5 meters. The summation of our y would be 1 meter plus 2 meters is 3 meters, minus 1 meter would be 2 meters. So here's this formula right here. But now, if we had multiple components, which that formula gets even more complicated looking, but it's not that hard to do. It just looks really complicated. It would be the summation of all x components squared, the square root of all, the summation of all x components squared, and the sum in all y components squared. So for our example, we already summed them all up. We would get the magnitude of r equals 5 meters squared plus 2 meters squared, the square root of that, and square root parentheses 5 squared plus 2 squared, close parentheses, is 5.39 meters. Okay, this takes a lot of practice to gain good understanding. Remember, you're just seeing this preliminary So you need more practice with it to get an understanding of it. But in summary, what you could do now for adding a lot of vectors to get the magnitude of resultant for a number of vectors is the first step. You find all x and y components of each vector. Then you sum all x components. Then you sum all y components. Then you find the resultant from p-sag of summed components. So the magnitude of the resultant equals the square root of the sum of the x components squared plus the sum of the y components squared. Okay. How about the direction of the components? Well, or the direction of the resultant. If we go back to our triangle, where we have, well, let's go back to our example where we had the 20 paces and 40 paces. We found the value of the blue. It was 44.7 paces. But the question is, what is this? Theta value. That would give us our direction. How do we find that? Well, if we look at the ratio of the opposite side to theta over the adjacent side, we can see that that ratio is 40 paces over 20 paces. Paces would cancel, so the ratio would just be 2. Now, what is the opposite over the adjacent? What trig function? It's tangent, isn't it? So tangent theta equals 2. So the question is, what angle in a right triangle any right triangle has a ratio of opposite over adjacent equal to 2. Well, we have tables. We have that we could look this up in for that. And these tables are now stored in your calculator. So we can just look it up in the calculator. And the way we do that is to look at a new trig function. Well, the inverse of the trig function. So tangent of theta is O over A. But the tan inverse of O over A is equal to theta. So to find our theta here, we're going to do the tan inverse of 2. And on your calculator, you just hit shift or second, tan inverse, and then parentheses 2, and we get the angle corresponds to 63.4 degrees. What if you have a ratio that's not tangent, or not opposite over adjacent, but is opposite over hypotenuse, or adjacent over hypotenuse? Well, what you do for that is you do sine inverse of the opposite over hypotenuse equals theta. So you would use, if you had opposite over hypotenuse, you would use sine inverse. Cosine inverse of adjacent over hypotenuse equals theta. And tan inverse of opposite over adjacent equals theta. Good. So, to sum up for our pirate hike, we have a delta S, our distance walked, equal to 44.7, no, I'm sorry, 70, right? No, 60. It's 20 and 40. 60 paces. That's our distance. Our vector displacement was 44.7 paces at 63.4 degrees. Okay? Quite a little pirate hike. Let's look at another example. All right. So a child playing tag runs 10 meters north, 17 meters west, 23 meters north, 5 meters east, and 24 meters south. What distance did the child cover? Well, that part is not hard. It's just a summation. 10 meters plus 17 meters plus 23 meters plus 5 meters plus 24 meters. 10 plus 17 plus 23 plus 5 plus 24 is equal to 79 meters. But how about, what is a child's displacement? Okay? For that, we have to go back to our list of things to do. So let's copy this first. So first, let's find the x and y components of each vector. In this case, the x component of going north 10 meters is plus 10 meters y, isn't it? 17 meters west would be minus 17 meters x. 23 meters north would be plus 23 meters y. 5 meters east would be plus 5 meters x. 24 meters south would be minus 24 meters y. And then the next step says to sum all the x components. So if we sum the x components, whoops, we get minus 17 plus 5 is minus 12 meters. And sum all the y components. Sum all the y components, we get 10, 33, minus 24 is 9, right? Plus 9 meters. So at the end of all the x and y's, we have a y component up at 9 meters and an x component at minus 12 meters. If I put these head to tail, I can see what my displacement's going to look like. Because I would start at the origin, go to the tip of the lath. So when we add these two up, 9 and 12, we're going to get this value of our displacement. Magnitude there. After we sum the x and the y's, we find the resultant through Pythagorean. Now the minus is just going to drop out. So, but if you put it in without parentheses in there, in your square root, it wouldn't work. So either make sure you have parentheses around just the minus 12, or just leave it off, the negative off. Come up with a value of 15. Well, 345, right? So we have our 15 meter displacement. But what is the direction? Well, the direction from the x-axis is that theta. Now, if I plug in theta is the tan inverse of opposite over the adjacent, I have 9 over minus 12. Now, in that case, you see that the calculator, when you put in 9 over minus 12, it's not going to know which is negative, like what you're doing. You're just saying, because you're going to do tan inverse, let's try it, 9 divided by minus 12. And that gives it gives you minus 36.9 degrees. But so the calculator doesn't really know. It's working in the first and third quadrants. So it's giving you this value right here is minus 36.9 degrees. Because it doesn't know, it just knows that because one of them is negative. So how do we correlate that to theta? Well, you could think of it as like finding a theta prime. Theta prime would be positive 36.9 degrees. And then we could see for the full half circle it's 180. So you could just subtract off 180 minus 36.9, and we would get 143.1 degrees. So your calculator gives you 36.9, but you can use that to figure out what it is from the x-axis. So in this example, we get 15 meters at 143.1 degrees. Let's try another one. Okay, so let's try multiple vectors, summation. So we're going to find the sum of the three vectors, A, B, C. A is 75 meters at 70 degrees. B is 80 meters at 60 degrees. And C is 135 meters at 120 degrees. So just drawing pictures of these three relative, 75 meters, that's 70 degrees. That has an AX and an AY. Because remember, the first step in summing these is to find the X, Y components of all of them. We also have 80 meters, a BX, and a BY, and that's at 60 degrees. And then 135 meters at 120 degrees. Okay, and this has a BX and a BY. So the first step was to find all X and Y components of each vector. So remember back that AX was the magnitude of A times the cosine of theta, and that would be 75 times cosine of 70 degrees, or 25.7 meters. And AY was A sine theta, 75 times the sine of 70 degrees, or 70.5 meters. Similarly, BX would be 80 times the cosine of 60, or 40 meters. It's not negative. BY would be 80 meters times the sine of 60, or 69.3 meters. BX, I'm sorry, this should be C, not B. CX would be 135 times the sine of 120, or 116.9 meters. And that makes sense that it's no, it doesn't. Oh, CX is cosine. Getting tired. Okay, cosine. Let's go back a minute. I want to check this. See, I was going too fast. BX is 80 times, we come back to the green, 80 times the cosine of 60, or 40. Okay, so I did those right. And then CX would be 135 times the cosine of 120, which would be minus 67.5 meters. I saw that that was wrong before because I knew it should be negative in the x direction because it's going this way. And CY should be positive, and that's 135 times the sine of 120, or 116.9 meters. The next step in the process is said to sum all the x components. So the sum of the x's would be 25.7 for the a's, plus 40 meters, plus a minus 67.5 meters. And that will give us minus 1.8 meters, not much in the x direction overall. When we sum the y's, we get 70.5 meters plus 69.3 meters plus 116.9 meters. Or 256.7 meters. So most of the movement was in the y direction. To get the overall displacement of these, or our overall r magnitude, we take the square root of the sum of the x's squared plus the sum of the y squared. In doing that, I get the value of 256.7 still. So it didn't, the 1.8 didn't do much to it at all. It's because it's just such a slight number to it in comparison to the 256. So I just made it up too. Now theta for the direction would be the tan inverse of the sum of the y's over the sum of the x's. And the tan inverse of the sum of the y's with 256.7. So we have a huge y and a little negative x. So our overall is going to be up like that. So we'll have to interpret the angle that comes out of this correctly. Because it's going to give me a negative angle. 256.7, whoops, 256.7 divided by minus 1.8, tan inverse of that is minus 89.6. Now, to really get the theta that we want, though, we'll have to do 180 minus that, minus 89.6, or 90.4 degrees. So it's almost all right along the y-axis. So if you can do that one, you can do all the work you need to with vectors. Because in this problem, you have to find the x components of each individual vector, the y components, and then you have to sum the x and y components. Then you have to do Pythagorean to get the magnitude of the resultant, and then you have to do tan inverse of the y's over the x's to get the direction. Okay, and that will bring you through topic 1.